Okay, sweet. So we are here and ready. Okay, so we're approaching 30 days for calculus stuff, so that's pretty exciting. Yeah, pretty exciting. Okay, so I think we'll just, as per usual, go ahead and go through Anki. We did add a lot of cards on. Was it Thursday last Thursday? Or last Wednesday? Oh no, that'd have been on Tuesday of last week. And so we'll go through those, and hopefully we'll be able to go through them fairly quickly. I know there are some new concepts in here for me. Pretty much all the trigonometry stuff that I did not remember. And so, yeah, we're just going to start there and get going along. I'm going to grab a soda real quick. Okay, sweet. Okay. Okay, cosecant reciprocal identity. So this would be cosecant equals 1 over sine theta. Okay, nice. Okay, cotangent reciprocal identity would be 1 over tangent. Yep, okay. So when finding the limit of the function, so if the function is not great for finding, let's see, what is a good way of saying this? If for some reason we can't evaluate the limit of the function directly, so say we plug in this variable or a value and does not get us a nice answer. For example, if it leaves us with dividing by 0, we can use the squeeze algorithm, the squeeze theorem, and this would take two functions. Let's see, how do we go about this again? Okay, I think what you do, is you take the, okay, I recall. Okay, so if you have a portion or a component of the function that is oscillating, okay. I know I have a question that like nails this point quite true, but this one isn't it. So the use of the squeeze theorem is if you have 3 functions, and each of them are, so you have from left to right is less than or equal to, less than or equal to, less than or equal to, right? Or if these functions are less than or equal to each other in like descending order. And you can derive the limits for the greater two functions, or sorry, the least and greatest functions. And those functions are equal, then by the squeeze theorem, you know that the center limit as well is also equal. Yes. By squeezing in two other functions whose limits are known equal at a point of interest. If the outer two functions approach the same limit, then the function between must also approach the same limit. Particularly useful for functions that oscillate or are hard to evaluate directly. Perfect. Okay, the secant reciprocal identity. This would be 1 over cosine. Tangent quotient identity. Is this... I think it's like sine over cosine. Yeah, okay. I'm going to send that through again because it was a little unsure. The cotangent, this would be cosine over sine. Okay, a good way to remember is that for the cotangent quotient identity, we have like cotangent cosine on top. Okay, how are limits expressed syntactically in the context of the integral symbol? The upper limit is on the upper side of the S, and lower limit on the lower side of the S. Yep. What is the definition for the sine trigonometric function? Its definition is the relationship in a triangle between, I guess, in a right triangle. Between the I guess not the relationship, but the ratio of the opposite angle over the hypotenuse on the unit circle. Okay, I think I just want a quick question on the unit circle, so I can help understand that in that context. I'm pretty sure the unit circle is the one in which, is it the radius is equal to pi? Or maybe the radius is equal to 1? Okay. Okay, the radius of exactly 1. Okay. Nice. Okay. I think for now, this is fine. Cosine would be a adjacent over hypotenuse, or x, on the unit circle. The chain rule is a way for taking the derivative of functions where you have a composite function. Tangent trigonometric function. This is opposite over adjacent. Okay. I'm going to send this one through again. Cotangent would be adjacent over... it would be opposite over adjacent. Oh, wait. Adjacent over opposite. Okay. Okay. Secant would be... Oh, heavens. This would be hypotenuse over opposite. Oh. Oh yeah, because secant is not sine. Secant is the inverse of the cosine. Okay? A polynomial is an expression with one or more terms. Okay, perfect. Oh, let's see. Where each term is made... Oh, okay. I probably should run through that again. And also... This is doing that one thing where it'll repeat it just over and over again. Okay, we'll just... Okay, so we'll do x to the 2 plus 2x minus 6. And we'll just say example. Perfect. Okay. The cosecant is opposite of the sine. So this would be hypotenuse over adjacent, or what would this be? X over y? Hypotenuse over opposite. Oh, sorry. No, that's x. When we have y and x, then that's hypotenuse over opposite. Okay, I've gotten that wrong again. You're not able to use the power rule when you don't have a composite function. When the function isn't a power of x, such as for an exponential, logarithmic, trigonometric, or implicit functions. When are you not able to use the the power rule? For some reason I was thinking the power or the chain rule. Okay. Process of rationalizing when finding a limit. This is when we try to remove the rational numbers, often by like multiplying by square roots. Yeah. The derivative of sine of x. Maybe negative. It was cosine? Oh, it is cosine. Okay, that was like, I was not sure. So the antiderivative of cosine would be sine then. The derivative of cosine would be, no clue, negative sine. Okay. How do you find a slanted asymptote? So you find a slanted asymptote if the leading coefficient of the... So slanted asymptotes are in functions where you have like some term, like a polynomial being divided by another polynomial. If the polynomial's degree is 1 higher in the numerator, then you know that you have a slanted asymptote, and you take use polynomial long division to figure out what that is. The antiderivative of sine of x would be cosine. Derivative of the tangent is no clue. Secant squared x, where cosine is not 0. In what situations we apply the squeeze theorem? When you have oscillating functions, or a term that oscillates within a function. Yeah, or when the function we're trying to get the limit for is like difficult to define, or sorry, is undefined at a given point, or just difficult to derive, or sorry, to get a limit of. Okay, bounded to between two simpler functions that converge at the same limits. Essentially, it's useful when okay. How do you find the horizontal asymptote for rational functions? If you have for a given rational function, if your power is the leading coefficient in the denominator is at least 1 more than the numerator, then the asymptote is 0. If it is if they're equal, then your horizontal asymptote is the quotient of the leading coefficients. Yep. Yes. Okay. What does applying the squeeze theorem look like in the context of working with a function that has a component that is bounded? It is bounded. It has a component that is bounded. I feel like oscillating is a better term here. It involves bounding the oscillating component. Is oscillating? Okay, I think we'll just run that one through again. This identity, this is the reciprocal of cosecant. The cosecant reciprocal identity. Okay, I think I need to recall that it's the identity. What is the double angle formula for sine? I think it's like sine of 2, or let's see, okay. So sine squared of theta is equal to 2 times cosine times sine. Okay, so that was incorrect. So sine of 2 times theta is equal to 2 times sine of theta times cosine of theta. Okay. This identity, cotangent equals 1 over tangent. This is the cotangent reciprocal identity. This is the secant reciprocal identity. This is the tangent quotient identity. Okay, tangent quotient identity. The cotangent cosecant Pythagorean theorem. So this is cotangent equals cosecant minus 1. I believe. No, 1 plus cotangent squared theta. Okay, so the Pythagorean identities are going to have the squared. We've got to remember that. And we know that for the presentation of these as a mnemonic, we know that the cotangent and the cosecant, like the ordering of cotangent and cosecant, also reflect the ordering of cotangent and cosecant within the formula. Okay, we're going to run that one through again. This identity, this is the quotient cotangent identity, or the cotangent quotient identity. Okay, and then another thing to recall is that the quotient, or I guess to realize, is that the quotient identities refer to cotangent or tangent, and then the reciprocal identities refer to all of the functions. The function is opposite over hypotenuse, or y in the unit circle. This would be sine. This identity, I do have a question regarding within the unit circle. Within the unit circle, why is it the case that sine refers to y and cosine refers to x, and then tangent refers to y over x? If that's correct, I may have mixed something up. Oh, wow. Okay. I've never made that connection before. Wow, that's really interesting. Because we're in the unit circle, our hypotenuse is always going to equal 1. And so we can, essentially remove that term. So the cosine of theta equals adjacent, which, yeah, so if we go to Excalibur and we have a circle, it's pretty bad. Oh, it's even worse. Okay, so actually I'm gonna switch up our colors here. We have our hypotenuse. We have our adjacent. Oh, maybe I should make him a little shorter. We have our adjacent, and we have our opposite. So being that the hypotenuse is always of length 1, if we have a cosine, which is, let's see, cosine, which is the adjacent over hypotenuse, or the sine, equals the opposite over hypotenuse. This is always 1. And so these terms can pretty much be, or not pretty much, they can be removed. And so that means our cosine would always equal the adjacent, and our sine would always equal the opposite. This being our adjacent, given this angle here of, was it theta? Or no, I think he's, yeah. I think he slashed through the, yeah, slash through the middle with theta. Okay. And then this over here would equal our, so this would be our adjacent, and this would be our opposite, which would equal y, and adjacent, which would equal x. Okay, I feel great about that now. Okay, so this identity, we'll move back here. This identity, we're just going to send it through because I opened it up. Okay, the tangent quotient identity, this would be tangent quotient identity can be thought of as y over x, or from what we just learned, this would be the opposite over adjacent, which would be the sine over cosine. Nice. Okay, I feel like that's locking in there. The secant trigonometric function, this is the opposite of the cosine, which would mean we're hypotenuse over adjacent, or 1 over x on the unit circle. Yep. Okay. What is the definition of the tangent trigonometric function? This is opposite over adjacent. I feel like we just answered that, though. Let's see. Oh, I think we probably we're looking at the maybe the alternate one, the flip one, the flip side, the reverse card. A polynomial is a expression with many terms where each of the terms have x or some variable associated with them raised to some power. Typically, actually always, they are of differing powers. Okay, where one term is a constant multiplied by a variable raised to a non-negative whole number exponent. Okay, so each term is a constant multiplied by a variable raised to a non-negative. Is really the non-negative a key part? That seems kind of odd to me. Oh, non-negative exponent. Okay, that's more reasonable, I think. Okay, for some reason I was thinking like a non-negative term, but I swear I'd seen negative terms in like algebra and stuff before, so okay, that makes a lot more sense. Okay, so feel good about that. The cosecant is the opposite of the sine, and so this would be hypotenuse over opposite, or 1 over y. Nice. The derivative sine of x would be cosine. You're not able to use the power rule when you don't have any exponents, so logarithms, trigonometric functions, and the like. Derivative of cosine is negative sine of x. Derivative of tangent of x is something like cosecant squared x and then some other stuff. Secant squared x, where cosine is not equal to 0. That one I think is going to be a little difficult to recall. Cosecant squared x. Okay. Yes. Okay. What does applying the squeeze theorem look like in the context of working with a function that has a component that is bounded? So I think for this one, we make two separate functions, where one we use the higher bound and the lower bound, and determine if we can evaluate the limits in that context. And if we can, then we can squeeze or I guess we don't squeeze literally, but like we know that the center function has the same limit. Between known values, multiplying these bounds by the shrinking term and showing both bounds approach the same limit, allowing the entire expression to be squeezed to that value. Okay, so I'm not sure if I deeply understand this. Could you give me an example of what is meant by approaching this both bounds approach the same limit? Walk through a couple examples of these problems. That would involve this. Okay. Cosine of 1 over x. We know that the cosine of 1 over x evaluates to negative 1 or 1. We multiply all sides by x2, so all sides of this guy. Okay. Take the limit of our outer bounds. Both bounds are evaluated to 0. And so we... Okay, trying to squeeze this won't work because we can't find two simpler bounds. So we have a counterexample here where the bounds don't match. Suppose we try the limit of x as it approaches 0 for 1 over x. Trying to squeeze this won't work because we can't find two similar bounding functions that approach the same number. The left limit negative infinity, the right limit infinity. So squeeze theorem does not apply. Let me know if you would like an example involving trig identities or one with inequalities that aren't oscillating. Could you give one where we have inequalities that aren't oscillating? Absolutely. Here's an example of the squeeze theorem where the bounded function isn't oscillating, but instead approaches 0 from both sides. We want to find the limit as x equals 0. At first glance, direct substitution fails because of the 1 over x squared inside the polynomial, inside the exponential. Okay, fair enough. We'll try to bound e to the negative 1 over x squared between simpler expressions. Observe that 0 is less than e to the 1 over x squared and is also, 0 is less than this, and this is less than 1 for all x that don't equal 0. Okay, because, yep, and then e is positive increasing. Okay, so we identify the bounds, and then we multiply the bounds by what we're looking at. Then we take the bounds, both bounds approach 0, so by the squeeze theorem, we can do that. Okay. Okay, I think, okay, so it involves bounding and oscillating a component. Okay, so this is slightly wrong, because this is like, just because of the counter, or not the counter example, but the example we received just barely, where we can have a function that is not oscillating but is still bounded. So being that this is the case, involves determining the bounds. Okay. Could you Okay. Let's see if we get a better answer this time because of the context that we've had previously. It means enclosing the bounded component between two constants, multiplying by a term that approaches 0, and showing both resulting bounds approach the same limit. Okay, I think this is preferable. Oh, heavens. Ugh. I did not like the fact that we just get this odd this copying. Okay, and then we'll say e.g. 1, or sorry, negative 1 and 1. Okay. Perfect. So I feel good about that. Okay, this identity, so this is the reciprocal identity for cosecant. The double angle formula for sine involves no exponents. So sine 2 theta equals 2 times cosine times sine. Nice. Okay, the cotangent cosecant Pythagorean identity is 1 plus cotangent squared theta equals cosecant squared theta. Perfect. This is the tangent secant Pythagorean identity. Tan squared theta plus 1 equals secant squared theta. Adjacent over hypotenuse, this is cosine. This is tangent. This is cotangent. The tangent secant, this is 1 plus tangent squared theta equals secant squared theta. The function is 1 over cosine. Okay, so this is the secant. This is the cosecant. The derivative of tan. Oh, I do not recall. So secant squared x, or secant squared theta, or cosine is not equal to 0. Secant squared theta or cosine is not equal to 0. Okay. Okay, so that took a while, but I think that was good because the trigonometric functions are ones that I needed to do but hadn't done yet, and so now I feel more confident in approaching these other ones. Okay, so we'll see. I mean, we're going to be ending here soon. But yeah, I think maybe we'll okay, so we're fine limited if it exists, if it doesn't explain why. So we're on 4. Find limited at 1, 2, 3, 4. Limit exists for the sum function is 0. If we attempt to plug in 0, we will get undefined. However, as we get arbitrarily close to 0 from the left and right direction, we converge on the same value. Therefore, the limit of this function taken at 0 is 0. Okay, so I don't think this is the correct way to say it. Now that I know the squeeze theorem, we can actually solve this the real way. Because though this, like, oh, maybe I'll zoom in here so it's visible. So the though this is intuitively correct, it's not well, yeah, though it's intuitively correct, I need a mathematical justification for this being the case. And the approach that needs to occur for doing this is using the squeeze theorem. So we know that cosine has a range of -1 to 1. And so we know that, -1 to 1. So we know that this will always be negative to +1. Okay? Okay, let's see. The limit exists for this function, and it is 0. And it is 0. If we attempt to plug in 0, we will get undefined. However, being that we have cosine here, cosine, well, cosine, multiply, well, being that we have cosine, an oscillating function, we have the setup to be able to oscillating function from values -1 to 1 to be able to apply the squeeze theorem. Perfect. We have the setup to be able to apply the squeeze theorem. All right. Nice. Okay. To do this, we create two simpler functions. That represent the upper and lower bounds for the cosine 1 over x a term. Following this, we multiply the remaining term x squared by x squared. This becomes the left function becomes the smaller function becomes the less than or equal to function. The smaller or equal function becomes negative x squared, and the larger or equal function becomes x squared. Being that as these two functions approach 0, we the result being that we can make a direct substitution. Substitution of our limit value. The value both functions evaluate to 0 given 0. Being that this is the case, we can squeeze these functions we can squeeze these functions. We can squeeze, I'm not sure what the language there. We can squeeze the limit of the center function. Being that this is the case, we know that the original function limit is 0 through application of the squeeze theorem. Okay, let's see if this is correct. I guess I already know that the limit's 0, so I guess this is just evaluating my correctness of description. So we'll go here. Okay, copy. You're very close. Multiplying the bounds by x squared. Okay. Okay. We multiply all parts of the inequality by x squared. Okay, so I'm feeling better here, but I would like to tune this, because as I've been learning more about math, it's clear that preciseness is incredibly important. And so I want to be sure that I'm being precise. Okay, so the thing that wasn't great was that we're not just multiplying the remaining term, we're multiplying the bounds by x squared. And these would be the -1 and 1. And then I need some better mathematical justification. So instead of saying make a direct substitution for our limit value, which is the mechanical action that I am taking, the way we do that is we just take the limit. We just say we take the limit. Even though that, like, this is actually what I'm doing, right? Okay. Okay, so, and I also need to know what is meant, like, by this inequality here. Let's see. You describe this inequality here. I'm not really familiar with this language in this context. I understand that we're doing some comparisons here. Are we saying this inequality is from the lower bound function and the upper bound function, or what would it be? Let's see. Okay, mean the yep. The entire inequality. So when we sort of expand this out, we call it an inequality. A compound inequality. Okay. So I need to learn about compound inequality. I did not have that language. Compound inequality. Oh, and I guess I could have done this right here, reevaluate my answer in this context. But I think I did well regardless. Okay. We'll say also the context above. Okay, nice. I feel like we are doing great. I feel like we're feeling good. Okay, I think we will end there for tonight. I'm super happy with where I'm at here. I feel like the trigonometric functions was a big thing that I needed to get over, even though in reality it wasn't like a huge thing. I think learning about the unit circle was incredibly insightful. Just the notion that the hypotenuse is 1 on the unit circle, so we can just pretty much remove that term for things like sine and cosine and think about cosine and sine in terms of like x and y is like super interesting. I don't think I've ever had that thought before. Yeah, so that was like really cool. I think, and then also learning about this like compound inequality was nice. So yeah, I'm just feeling really confident on the trigonometric functions, and had some really cool insights. And then, yeah, and then I also like that we're getting a little bit more precise with my language, to make my statements incredibly clear and like pretty rigorous. So yeah, very good session. I will see you guys tomorrow.